Okay. Can everyone see the paper on my screen?
Yes.
Okay. Awesome. Well, thank you very much for joining. Today I'm going to talk about this paper that was I'm not sure if it was published or it was submitted at NeurIPS 2022. It's titled Active Bayesian Causal Inference. And we will go over this together and talk about their approach and what they basically did in this work. In this paper, they basically took an approach of actively making queries to perform two tasks. One of them causal discovery. So the assumption here is that the causal graph is not known. So they developed an algorithm that would do two things. One is to learn the causal graph and also um, basically perform interventions and sort of quantify the causal relationship between different nodes and be able to obtain interventional data from the graph. So as they sort of explain here, in their two-stage approach, one of them is sort of inferring the causal graph and then estimating the causal effect of interventions. That's how they do it. Just as an overall picture, they don't focus on learning the full graph. So their purpose is basically to partially learn the graph, just have enough information about the true causal model to be able to make queries and be able to estimate sort of interventions. And they take a Bayesian approach in order to do that. They use uh, Bayesian inference and also Gaussian processes. And at each time step and at each intervention, they have a utility function that they go over and they want to maximize that utility function and they update their information after each cycle. So they talk about that in more detail, just to have like a quick overview of what they basically propose in their work is first they start with a simple Bayesian model on observational data. So at the beginning, no interventions, just uh, basically samples from observational data, and then they perform interventions or do calculus at time t, and based on that they and they talk about the notations as well. We will go through that, assuming that M star is the true causal model. So based on that they try to sort of um, mm, produce interventional data from the true causal model after the interventions that they performed, and after obtaining interventional data after the interventions they perform, they update the posteriors of their basically Gaussian processes, and after that, based on the queries they have, they call it target causal query, they inform their next experiment. So their experiments updates as well after each cycle and intervention they perform. So with a better experiment, and they do this using maximizing a utility function, they sort of go through this cycle again and perform interventions, update the posterior, updating the experiment, and this is what they call active Bayesian causal inference framework. So just this was an overview of what they basically proposed here. But in order to get us started, they call their algorithm ABCI, Active Bayesian Causal Inference, which, as they describe it, is a fully Bayesian active learning framework for integrated causal discovery and also reasoning, causal discovery and reasoning. In their approach, they use a class of causally sufficient nonlinear additive noise models, which they use Gaussian processes for that. And also regarding experimentation that they perform, they sequentially perform experiments that are maximally informative about target causal query, and they talk about the different causal queries that they perform. And they collect corresponding interventional data, update their belief to choose the next experiment. So they also update the experiments after each intervention. And through simulations only, they demonstrate that their approach is sort of better than only using observational data and also other methods. So they don't sort of perform experiment on real world data sets. They only have one. They only have two sets of synthetic data. Uh, One with allowing interventions on all the nodes in the basically when they identify the graph. In another one, they don't allow performing interventions on all of them. But they sort of in the experiment section show that their approach has advantages to the previous methods. Just as an introduction, overall introduction, they cite some basically work about causal reasoning, and they mention that most of the related work either focus on causal learning, causal discovery, or basically causal reasoning, or trying to make inference based on interventional experiments that are performed. And this is one of the few works that tries to merge these two together. So this is one of the novelties that they have in their work. Um, and they start with basically very basic introduction, and then they talk about how in the relative approaches to causal discovery, focus is usually on learning the full causal model. So a lot of basically effort is usually spent on learning the full causal model instead of just learning the sort of the important parts, or based on the query that they have, just learning the part enough to answer the causal questions. And they mentioned that there are two disadvantages in trying to learn the full causal graph. One of them is that basically wasting the samples on learning the full causal graph. At least a lot of samples is required, so a lot of sampling would be required in order to do that. And also, if we have limited observational data, or we have small amounts of data, there would be a lot of errors in sort of trying to find the true causal model, because with a limited sample, we may have multiple DAGs, and they sort of may not show the true representation of the true causal model. So they propose ABCI, active Bayesian causal inference, which the basic approach is to put a Bayesian prior over the causal model class of choice, and cast learning problem as Bayesian inference over the model posterior. So because they don't want to learn the full graph, they take a Bayesian approach that after each cycle, their prior would be updated. So the prior is Bayesian, and then based on the interventions they perform, their posterior becomes updated. Um, One thing they introduce, as I mentioned, is having a target causal query, and they explain that in the next section what causal queries they use, which essentially is a function of the causal model that specifies the set of causal quantities that they are interested in. So this is one of the important part of their framework. Also, the model posterior. Is there any question? Um, the model posterior together with the query function induces a query posterior, which represents the result of Bayesian learning procedure, which will be downstream used in the next cycle as well. So they have a Bayesian optimal experimental design approach, and then they update the belief by computing the posterior over causal models and queries, and they use it to design the next experiment. And they have formulas and, as I mentioned, a utility function that they try to maximize to design the next experiment in the next cycle. So it is a very interesting work, and it sort of uses many different concepts all together to come up with this algorithm that they used. So they use a causally sufficient nonlinear additive Gaussian and noise model, or using Gaussian processes. So this is one of the main basically important approaches they take. They instantiate their approach with the class of Gaussian processes, which is nonlinear, and it is an additive Gaussian noise model. And they also they actually refer to another work that is called differentiable Bayesian structural learning, DIBS, and they use part of this DIBS approach in this work as well. So they use this approach employs a continuous latent probabilistic graph representation. So they use this DIBS algorithm as well. So when they want to call their algorithm, they call it GP DIBS ABCI. So it is sort of three different pieces together: Gaussian processes, this one, and then their ABCI based, which is the active learning part. So in the next three sections, other than the related work, in section 3 they propose ABCI, which is a flexible Bayesian active learning framework. And then in section 4 they talk about the Bayesian optimization, and also the Bayesian framework that they use, Gaussian processes and such. And in section 5, they sort of talk about, with different sort of sample sizes and observational data, how basically in terms of graph and learning the full graph or learning partially the graph. Also, they talk about the distributions and different things they use in their approach. And then after that, they have an experimental section that they show how this approach sort of is superior to other methods and also other type of experiments. Regarding related work, as I mentioned previously, the works are either focused on causal discovery or only on causal reasoning. There is another work that they sort of refer to here, which is very important. I think, I'm not sure if I highlighted that here, but there's another algorithm called ABCD, and that's sort of, they got the idea of sort of taking this approach from that paper, which I think we will get to further down the line. But they after talk about some of the similar works. I think the paper is this one, Agrawal et al. Well, first of all, they talk about another study which also uses active causal inference approach by Tigers et al., which they consider experimental design for learning a full SCM parameterized by neural network. So it's a little bit different. But there's another work they cite here, Agrawal et al. From MIT, actively learning a function of the causal graph under budget constraints. And they say that this work is very similar, but in this work they do not use causal mechanisms, and it's only for linear Gaussian model. So if I click on this over here, this is the name of this paper, ABCD strategy, budgeted experimental design for targeted causal inference discovery. So this is only for discovery and not reasoning, but they got the idea from here. Another work that they cite here is by Rubenstein which they perform experimental design for learning the causal mechanisms after the causal graph has been inferred. So here the causal graph is known, but they have an experimental design that sort of performs causal reasoning. So in figure one, they have the overview of the framework. So it is like a sequential experiments that are performed at each time t. They use a Bayesian experimental design based on the belief at that time point or at that stage that they want to maximally uh, they want to choose a maximally informative intervention a of t. So a of t is the intervention at time t, and they want to perform do calculus on that Bayesian prior, and then based on that they want to collect finite data samples from interventional distribution induced by the environment. So they want to based on an x's are the basically the um, observational data that are present, and we want and that they want to sort of perform intervention on, and based on that they obtain little x, which is their interventional data. And after that, so capital X is their observable variables, small x is their interventional data collected, and they pass that on based on sort of that Bayesian framework that they have. They infer posterior over a target, actually before that, and based on that and prior this distribution, they make inference. So they would update their SCM or a structural causal model based on this interventional data, and based on that they make estimations based on target causal query. They infer posterior based on that, and they express it as a function of the causal model. And for example, they may be interested in learning a graph with the presence of certain edges. So they may have like an idea of how the graph may look like, but not exactly. They just want to see what is the relationship between a few nodes, not the full graph, and this is where it can be useful. So this is one type of query, and they actually compare these approaches together. But one of the queries can be learning just partially, or another query can be trying to learn the full graph, the full SEM, or another approach may be a collection of interventional distributions or treatment effects, or any combination. So they talk about that more, and that informs their decision on the next experiments they want to do, and they just repeat the cycle. They start with the notations. So I'll spend a few minutes just explaining what variables they are using. Um, um, Uppercase X uh, and lowercase, and uppercase X refers to the observational data, and the lower case x refers to interventional data that is generated. If they are bold, it means it is referring to vectors or sets, basically in the equations, and p refers to distributions or densities. For their causal model, they use a structural causal model approach, and from a Bayesian perspective, an HCM can be viewed as a hierarchical data generating process involving latent random variables. So they define SCM as SCMM that has endogenous variables X and unobserved exogenous variables U's. And they sort of formulate it this way, with PA being the parent of a particular node I, and F being the deterministic function of basically in the causal relationships. So they explain that. Um, and also it is obviously acyclic. Regarding interventions, they sort of define it as any intervention to be external manipulations to one or more of the causal mechanisms in equation 3.1. And they use Pearl's do operator to denote the interventions that are performed on basically any observational data. And they use, after the interventions are performed, they have an interventional distribution, which is shown this way: P of do on A, and A refers to that particular intervention that is performed. Then regarding sort of Bayesian approach with respect to causal models, they have the Bayes theorem formula here as well, which is very basic. M star is the true causal model, and M is the sort of the prior, or the sort of the causal graph that we're trying to estimate. Then regarding Bayesian causal inference, um, they they talk about how trying to focus, as I mentioned previously, um, focus on learning the full graph. It may be a wrong approach because it may lead to uncertainty and basically errors in learning the graph. And that's why they want to learn an important, or uh, part of interest in a graph that sort of is able to solve the target causal queries, which is basically this function Q is the function for this target causal query, which is applied to this M to obtain Y. And here they have 4 different causal queries that they sort of in their experiments use. One of them is the query of interest may be causal discovery, which is learning the full causal graph G. So this is one type. Another type is partial causal discovery, which is learning some feature phi about the graph. So maybe a particular sets of edges. Let's say, for example, in real world scenario, they want to select impact of smoking on cancer, or basically blood sugar, diabetes, things like that. So they may not need to know the full causal graph. Causal model learning is another query, which is learning the full SCM, structural causal model, also, or maybe causal reasoning, which may be learning a set of interventional variables induced by M under do calculus. So they initially they perform interventions based on this. So after,
Morteza,
yes,
may I ask a question?
sure.
Thanks for selecting this nice paper, and it's very relevant to your work too, right? If you remember, we had discussion like when you started about separating this causal query from learning the causal model, right?
Yeah.
And I like this categorization of these causal queries. And it is also relevant to Shahryar in Shahryar work. So he has also a similar setting where he learns a causal performance model, but the goal is to optimize performance. So is a sort of causal reasoning, the last scenario, right, of the causal queries. But I was wondering, causal discovery and causal model learning, how these are different.
Yeah.
Is just the representation is different between these two types, or?
Yeah, sure. I think here they want to learn a structural causal model, which I believe, I mean, I may be wrong, but it's more involved with learning the relationships between the nodes instead of, for example, in the causal graph. And I think, let me see if they have like a good example in, well, not this one, but for example, learning the causal graph G is like learning this, that, for example, this node is parents to these two, but learning the SCM is talk about quantifying the relationship, meaning, for example, x3 is like 2 times node of x1 plus a noise. I think that's what they mean by learning SCM, meaning quantifying their relationships.
I
But
see. Yeah, that makes sense.
yeah, it's like having equations for the relationship between nodes. But learning G is just knowing which node is the parent of which other node, and that may be just it. Um, I'm not sure if there are any other uh, comments or suggestions, but regarding that one, I think this is how they introduce this. But um, after the causal query is performed, they sort of update the Gaussian their sort of Gaussian process, and it sort of extends to their next learning goal, which is query posterior. So there's a query prior, and then there's a query posterior, given the Bayes theorem here, and this is the formula for that. So this is the distribution, and y being the query distribution of y, or the query given data. This is the formula for that. So this is one important part that they talk about. Also, this algorithm is not is very computationally expensive and hard, and they talk about in the discussion as well, because there's a lot of estimation has to take place. Also, because they don't know the causal graph, there's a lot of sampling that has to be performed, a lot of iterations. So this is definitely a hard computation problem, but they try to use Monte Carlo simulations and sampling to sort of overcome that, but still it is a very computationally expensive approach. Then they talk about identifiability of the causal models and the queries, and they define identifiability as the ability to uniquely recover the true model in the limits of infinitely many observations from it. And they additionally talk that basically mention that if we can solve the identifiability problem, then the posterior, or this sort of then the posterior, um, which has this formula, will collapse and converge to a point mass on their respective true values of m star, which is the true causal model, and q m star, which is the sort of query based on the true causal model. So this identifiability problem sort of assumption is, if it is satisfied, then if the algorithm for estimating this Bayesian approach will collapse. But if they don't have that identifiability problem, basically assumption solved, then it's going to be a little bit difficult for the algorithm to converge. But they do mention that even in that case, it may still collapse sometimes. For example, if the Markov equivalence class, or MEC, is identifiable, and they talk about that too. So there are some limitations in the approach that they take here. Then they talk about the sequential interventions, how they perform that. So they sort of define sequentially designing experiments in the form of interventions, AT, which is intervention at time t, and at each step t, the outcome of experiment. AT is a batch of xt, which are interventional samples of observations from the true interventional distribution. So they define the interventional distribution this way, which is based on this Bayesian, or the based on the probability of performing intervention on data given the true model, and x of t are the interventional samples that are generated. And then based on that, they design next experiment to be maximally informative based on target causal query Y, and they listed the causal queries here, so there were 4 up there. And so this is the formula for that. They want to sort of maximize the information, the sort of, which is formulated as maximizing the myoscopic information gain from the next intervention, that is the mutual information between Y and the outcome of X of T. So this is basically how they want to do that. The I refers to information gain, and this formula is used for that. And X of T follows the predictive interventional distribution of the Bayesian causal model and ensemble at time t minus 1. So they want to show, for example, next they, I may be wrong, but they perform a prediction for next iteration, and based on that they compare those two, and that's how they obtain this X of T, which helps them in experimental design for the next step. So they compare each step with the step before it or a step after it, to sort of make sure the at that step the experimental design will maximize information. And then they collect experimental data and infer target causal query in a efficient goal-oriented manner. And they talk about that in a bit more. So after this section, they talk about their ABCI algorithm and framework and what the steps are involved in this. The first step, as we mentioned, is having a class of causal models to consider. So equation 3.1 that they show here. So this is like, they start with this. They start with having like a basic framework or SCM based on the information they have. And after that, the types of interventions, AT, they consider at each step, and the corresponding interventional likelihood in equation 3.4. So here in 3.4, they talk about the interventions and basically how they define the distribution for these interventional data. So that's the next step. And then after that, they want to maximize the information gain. And here, X of T is this is how they gain information about sort of maximizing basically designing their next experiment. That's what the next step was for. And then maximize information gain for experimental design. Then they talk about their model class and parameterization. I probably don't have to spend time here because this is just defining and mostly background things, but they consider a nonlinear additive Gaussian noise model, and U is the basically unobserved variables, and PA refers to the parent of particular node I, and F is the function that is smooth and nonlinear, and UI being the basically unobserved variables but mutually independent. The way they parameterize their model, M is this way: model M, G, F, and sigma squared, G being the graph, F being this function, which is a vector of functions d1 over parents sets implied by G, and sigma squared is the Gaussian noise variance. So this was regarding the model parameterization. Interventional likelihood, they consider hard interventions, and in the discussion section they talk about they only use hard interventions, but soft interventions could also be used as like future work, but they only consider hard interventions of this form of due calculus. And they also provide the formula here as well for the distribution of the interventional data based on the given graph. And this is how they obtain the likelihood of each of the interventional data. So this is interventional likelihood. This is the formula how they perform the calculation to obtaining that. So this was regarding interventions. Then there's a structured model prior and there's the model posterior that they talk about. So their model prior, basically they divide the nodes into two groups. One is root nodes and one is non-root nodes, and they take different approaches for them. But overall, they integrate them together in this formula 4.4 into one, basically, uh, distribution model, distribution for the model, but they take different approaches, basically for them. Um, they mentioned that to specify their prior, they distinguish between root nodes for which there is no parent and the fi function is constant. Um, and for non-root nodes, they sort of uh, show them as x sub j. So they talked about that a little bit more further down the line, but this is how they define their model prior based on a sort of a distribution over the model based on this calculation between root nodes and not non-root nodes. And for model posterior, they, based on the interventional data that they obtain, they update their belief as well regarding the M star, which is the true causal model, which is here is the Bayesian approach. Also based on root nodes and what happens to root nodes and non-root nodes. And for root nodes that are part of this group, the posterior is more straightforward because f is constant, that function is constant because they don't have any parents. But for non-root nodes, because they do have parents, uh, they sort of take this approach. The posteriors over graph for non-root nodes has this formula, so it's a little bit different. But for root nodes, they mentioned that they place conjugate normal inverse gamma, which is this funny looking, basically, um, representation here. And there are also hyperparameters associated with that, and they talk about each of these hyperparameters in the next section. But um, just the point is that they treat root nodes and not non-root nodes differently. And after they explain the framework, they talk about challenges that were faced, three challenges that they sort of overcame in developing this framework. One challenge is trying to marginalize out the functions. So this being the marginal likelihood of the interventional data given the graph, which requires evaluating integrals over the function domain. So we're trying to solve this integral, and this is not easy to perform. But they mention in order to overcome this challenge, they take a Gaussian process approach, and they use Gaussian process, which is nonlinear, that which also offers conventional analytical properties. So, in order to solve this integral, they place a GP with mean of 0 and this variance prior on this, basically, distribution of function f, given the graph, where this k is the covariance function over the parent of x with kernel parameters small k, or I think this is kappa. So they use GP approach, and then for for each of the GP hyperparameters, they introduce gamma distribution for basically the mean and the variance for sigma squared and kappa. So they introduce sort of gamma distributions for those to collect the parameters. So they talk about these sort of approach, how they try to, in general, overcome this, basically solving this integral. So this was one of them, one of the challenges they faced. The second challenge they faced was marginalizing out the GP hyperparameters. So basically, they mentioned that it was intractable for that integral to be performed based for the hyperparameters of the Gaussian process model, and in order to solve that, they used a maximum a posteriori or MAP point estimate approach to solve that. So this is how they have the formula for that, and they have the sort of distribution here for that as well. So this is the method they use to solve the problem of marginalizing the hyperparameters. And the third and final challenge they faced was marginalizing out the causal graph. And they mentioned that it solving this, which is the distribution of the interventional data, and solving sort of this summation becomes intractable for D of greater than 5 or samples of greater than five variables as a number of DAGs grow up. I think D here refers to number of nodes. As the DAGs grows super exponentially. So in order to solve that, they use this DIBS approach, which is the differential approach that they have developed before to solve that. And the problem, because it becomes simple down to solving this expectation. So they talk about a little bit more details on that. Then after explaining the challenges, they talk about trying to approximate their experimental design using Bayesian optimization, and this is how they call their method sort of Bayesian. The goal of the in section 3 was to perform experiments at time t that are maximally informative about the target query by maximizing the information gain based on the collected interventional data. And they show in the appendix that there is a utility function, which is really important, which should be maximized. So this utility function is based on, I think this is the Hamiltonian of the sort of interventional data given the observational data, and this utility function should be maximized. And this Hamiltonian shows the differential entropy of the experiment outcome, which depends on intervention A and is distributed as explained in section 3. So this is like a surrogate objective that can be estimated using a nested Monte Carlo estimator, as long as they can sample from sort of from the data. So this utility function, now sort of merging this utility function with the causal queries that they showed, they sort of produce these different different types of utility functions. So UCR is the utility function for causal reasoning, for example, and this is how they show the equation basically here. And they have different sort of types they perform experimentation on. They also have UCD, which is the utility function for causal discovery, and they show the sort of equation for it as well. UCML is another sort of utility function for the basically query that they want to perform based on the objective they want to have. So after having this utility function, they want to find the optimal experiment that requires jointly optimizing the utility function corresponding to their query with respect to two things: set of intervention targets I, and also corresponding intervention values xi. So what nodes they want to perform intervention on, and also what values they want to perform intervention. So here I star is also like an optimization problem, a bilevel optimization problem, trying to sort of optimize what nodes to perform intervention on and also what values to perform intervention on. This is how they basically use Bayesian optimization to inform their basically interventions, and in the appendix they show how they do that. So for the interest of time, I skip to the experiments. Hopefully in about 7-8 minutes I can explain this, and then I'll stop for questions. So this is the algorithm. They show basically how they performed how they implemented the framework they talked about. When they performed experiments, only they performed that on synthetic data, and on but they divided that into 3 different utility functions. UCD refers to utility function for causal discovery, trying to learn the graph. UCML, causal model learning, and UCR, causal reasoning. And causal reasoning, they uh, is the situation where they know the causal graph, but they want to just uh, perform interventions and learn from the graph. And they have 3 different data types. One of them is I think one of them is samples from an observational distribution, so no intervention. So this is one type of the data they use. Second type of data is to performing any interventions at random, and basically they call that rand fixed. So this is another type of data that they have, based on a uniform distribution. If I'm not mistaken, there should be one additional data type, which is here. Yeah, just the rand, which is drawing from a uniform distribution, um, without having any interventions. Then they perform interventions on these graphs with size of 20. So the graphs have 20 nodes, and they also, for these graphs, they are Erdős-Renyi random graphs for different with different sizes. Now for metrics, so these are the experiment results. So for metrics, they use SHD and KLD and AUPRC. So briefly, I'll explain what they are. KLC is callback library divergence, which is between the true query distribution and the inferred query posterior, KL. And they report query KLD estimate, a KLD estimate for target interventional distributions. So it's basically they show here based on interventional data, and they also use SHD, which is a structural Hamming distance, which is commonly used for causal discovery metric, which is the area under the precision recall curve. So AUPRC is the precision recall curve over here. And looking at these 3 different graphs, we see observational, basically this algorithm, how it's performing on observational data, which is the pink line here. UCD performing very good in almost all 3 of them, and CD is for causal discovery. So their algorithm performs very nice in causal discovery based on these 3 metrics. Very good here and very good here and there as well. They perform addition. So in these experiments here are for only causal discovery. They didn't want to learn relationships between the nodes. They just wanted to basically they didn't want to quantify relationship. They just want to learn the causal graph. So utility function for causal discovery worked very well here. In the second type of experiment they performed, they had a known causal graph, and there are two sections to it. In one part, they were able to perform, on the left side, they were able to perform interventions on all of the nodes. In the right side, in this experiment, they were able to perform experiments on all the nodes, exception of X3, and they compared different utility function sort of outputs for that, and they see UCR, which is the function for causal reasoning, basically performs very good over here, but over on the right side, not very well, only after basically a certain number of experiments. So at the beginning, it doesn't perform very well when they're not able to perform experiment on all of them. So that was regarding experiments. Just for 2 minutes, I wanted to talk about sort of discussion and future work. Um, this algorithm that they use here, there are some assumptions. First of all, in this framework, it excludes heteroscedastic noise. It is unobserved. They assume unobserved confounding. They assume excluding heteroscedastic noise. They also assume cyclic, basically, actually, it excludes heteroscedastic noise, it excludes unobserved confounding, and excludes cyclic relationships. On the experimental side, they only considered hard interventions, but for some applications of some soft interventions are possible. On the query side, they only considered interventional distributions. However, there may be some other types of basically queries that can be performed, like counterfactual queries, such as effect of treatment on the treated, which they did not consider. And there were some violations that basically in the sort of interventions that they perform may have happened, but for example, they mentioned actively performing interventions allow for causal learning even on their causal sufficiency violations. So they say this approach would overcome some of the limitations or violations that would usually occur with causal learning. So this ABCI can be helped with that. Then they talk about how this can be combined with transportability and external validity concepts that in causal inference that can be used. And also they mentioned that in real world scenarios such as biological networks, active interventions are possible, but only at significant cost. And this framework, because it's not learning the full causal model, can help in that as well. I'll stop for questions. I think we have around 5 minutes. Hopefully this was a interesting work and would inform future experiments as well.
Thank you, Morteza. It was very good.
Sure, thank you very
I
much.
also like the experiment, the synthetic experiment that they ran. It is quite useful for, developing approach and debugging it.
Are there any other questions or comments?
Thank you, Morteza, for your great presentation. Thanks.
Thank you. Okay. If there are no comments, I hope everyone has a great Friday.
Thank you.
Thank you, everyone.